Welcome back to linear algebra. Let's jump into Anki. One flashcard. What are the numbers in a matrix called? They're called entries. All right, that's it. Okay, doke. What did we learn about yesterday? All right. Let me think. We expanded the equivalence theorem to 6 basically points that if we know one, we know all. And they are a matrix is invertible. The equation AX equals 0 has only the trivial solution. The reduced Roy echelon form of A is I. A can be represented by a product of elementary matrices. AX equals B. All B column vectors that are m by 1, or n by 1. Yeah, m rows. I think so. The linear system is consistent, meaning there are not no solutions. There is one or more solutions, and we know also that AX equals B for every B. For every B, there is exactly one answer or one solution set. So there's the equivalence theorem updated. We also learned that if A and B are square matrices and their product is invertible, then the factors are both invertible as well. Is that basically everything? There's something else I'm forgetting. I don't know. Yeah, I'm sure I remember. Right. We also learned that if we know that A times B equals I, well, then we know they're inverses of each other. And so we also know that B times A equals I. So if we know one or the other, we know both. And we're just about to get into this thing called a fundamental problem. So I'll be back in a little bit. It looks like I'm about to finish reading right now, so I'll be back in a little bit. All right, so I finished reading the chapter or the section 1.6. So a fundamental problem that they're referring to is you've got a matrix, right? You want to know all the values of B in which the equation AX equals B is consistent. That's a fundamental problem. If the coefficient matrix A is invertible, then we know the matrix is consistent for all possible values of B from the equivalence theorem. But if it's not a square that's invertible, we can use elimination. So we partition and we augment the matrix. We get it into reduced Roy echelon form, and then go from there. So you'll probably end up with like a bottom row that is all zeros, and you need to show that like whatever's in that B in the bottom row, bottom right hand corner, it needs to be not equal to, or it has to be equal to 0 for the system to be consistent. Because if you have zeros in the coefficient matrix in a row and then something that's non-zero in the B for that same row, then it's not no solution. It's inconsistent. So I think a lot of this stuff will probably become clearer as I practice them. So I'm not gonna waste any time, and I'm just gonna get right into doing the practice problems. So I'm going to go start doing some, and then I'll be back to recall at the end of the day. So talk to you about. All right, guys. So first question, we get a matrix. It says to solve using the inverse. So I had to think about it for a little bit, but then I was like, yes. Okay, check if it has an inverse. It does. Okay, then if matrix A is invertible, then the system AX equals B has exactly one solution, and we can multiply both sides by on the left by the inverse of A to get X equals the inverse of A times B. So find the inverse of A, and we multiply that by B. There's your solution for X. Question 2. This was, you got a matrix, and here are 2 solution sets. Solve them all at the same time. So get it down to reduced echelon form, and here you go. Then here's solution set 1, and here's solution set 2, and so next will be 13. I'm doing it a little different here. I was about to do every other odd or every odd, and it was just like, why would I do that? That's maths practice. So I did 1 from the first section, which was 1 through 8, was solving a linear system using matrix inverse. The second set of questions, 9 through 12, is about solving multiple solution sets at the same time, by using reduced echelon form, Gauss-Jordan elimination, essentially, with multiple partition matrices. And then 13 through 17 will be the next one. This is determine conditions on the B's or BI's, if B sub i's, if any, in order to guarantee the linear system is consistent. And this is the last thing we were just talking about today. This was the fundamental problem type questions. And then there's going to be another small section, and then the proofs, true, false, working with technology. So this is a really quick section. Yeah, that's it for today. Talk to you tomorrow. See you.